In this video, we are going to be talking about di and polybasic acids and di and polyacidic bases. In the previous one, we discussed the example problem, and even before that, we discussed the concept related to that particular example problem. Definitely let me know if you need help with any other concepts, or just comment below if you found this video helpful, because that definitely helps me keep going. So di and polybasic acids. I'm going to start talking about that first. So let's talk about four of these examples. Oh no, three of these examples. So you have COOH taken twice, which is oxalic acid. And then you have H2SO4, okay, which is sulfuric acid. I know you know that. And H3PO4. Now, what is the one thing all of these have in common, apart from the fact that they're acids? So, if you notice, the number of protons each of these possess is more than one. So, oxalic acid can give up two of the protons. So, it's essentially COOH. So, this is oxalic acid, and it can give up both these protons. Similarly, sulfuric acid can also give up both of these protons. So, when you have ionization happen, you have 2H plus SO4 2 minus, right? You've always written that, but basically it is able to give out two protons. Similarly, with H3PO4, which is phosphoric acid, it has the ability to give out three protons. So it would be 3H plus PO4 3 minus. Okay, so these acids which have more than one ionizable proton per molecule are called polybasic or polyprotic acids. So essentially they have more than one ionizable proton. The word ionizable is really important. It could very well have a proton, but it might not get ionized. So it's very important for the proton to be ionized, and it has to have more than one ionizable proton. That's what makes it a polybasic acid or a polyprotic acid. So let's consider the example of a dibasic acid. Okay, so you have H2X. Okay, so the ionization, the first step would be H2X is going to give us H plus HX minus. That's the first step. The second step would be HX minus is in equilibrium with H plus X minus. Okay, so you have H2X is in equilibrium with H plus H. So it's giving out the first proton, and then it's giving us the second proton. So the overall reaction would be H2X is in equilibrium with 2H plus X minus. So that is the overall reaction. Now let's consider the equilibrium constants for each of these. So Ka1, since it's the first step, we're going to consider it Ka1 is equal to concentration of H plus into concentration of Hx minus divided by concentration of H2X. So you know what I'm going to go to do next. Ka2 is going to be equal to concentration of H plus into concentration of X minus divided by concentration of Hx minus. Okay, so this is Ka1 and Ka2. So this one is essentially the first ionization constant, and this is the second ionization constant. What is it called? The first ionization constant, and this is the second ionization constant. And it's important to remember these two terms. Now let's do another example for funsies. We're going to talk about H3PO4. So it's going to be how many reactions? If you said 3, you are right. So H3PO4, H plus H2PO4 minus H2PO4 minus is going to be in equilibrium with H plus HPO4 minus 2, because it lost the first two protons. And then you have HPO4 minus 2 is in equilibrium with H plus PO4 minus 3. So essentially the net reaction would be H3PO4 is in equilibrium with 3H plus plus PO4 3 minus. So in this case, it's going to have how many ionization constants? 3. So the first one, Ka1, let me write it here because space. Ka1 will be equal to concentration of H plus into concentration of H2PO4 minus. Okay, so this divided by concentration of H3PO4. Ka2 would be equal to H plus, concentration of H plus into concentration of HPO4 minus 2 divided by H2PO4 minus Ka3 will be equal to concentration of H plus into concentration of PO4 minus 3 whole divided by concentration of HPO4 minus 2. So Ka1 is going to be the first ionization constant, Ka2 is the second ionization constant, and Ka3 is the third ionization constant. Now the net equilibrium, if you remember from the previous video, we had spoken about the net equilibrium for a particular reaction would be, so the net equilibrium for this would be Ka equals to Ka1 into Ka2. Oh, I just realized you can't see what I was writing. Awkward. So Ka is equal to Ka1 into Ka2 into Ka3. So that's the net equilibrium. If you remember, the net equilibrium of a particular reaction is equal to the equilibrium constant of individual parts of the reaction. That's what we learned in the previous video. And if you notice, you would get to the same equilibrium equation as you would for this when you multiply this with this with this. Okay, so that is what you need to know. Now let's look at these values of oxalic acid. So in your textbooks, you've been given a bunch of examples, but I just wanted to pick one. So pick the oxalic acid. So oxalic acid has a Ka1 of 5.9 into 10 to the power minus 2. Ka2 is 6.4 into 10 to the power minus 5. So what does this mean? Right, so essentially what's happening over here is Ka1 is significantly higher than Ka2. I know these are really small numbers, but in comparison to each other, this is significantly lower than this one. So essentially what is observed is the value of the ionization constants, that is, let's say for phosphoric acid, so Ka1 would be greater than Ka2 will be greater than Ka3. Okay. So the ionization constant value is decreasing. Okay, and this is because it is more and more difficult to remove the proton. Now in this case, H3PO4, it's easy to pull out the proton, right? But when you have a negatively charged ion, it's more difficult to get to this H2. Right, and similarly it has a more negative charge of minus 2, then it becomes automatically even more difficult for us to get the hydrogen atom out. So essentially what's happening is when you have a negatively charged ion in this, as in this case, it's making sure it's holding on to it. This means that it becomes more difficult for it to get removed, right? So essentially that is why you have the value of the ionization constants decreasing as you go from Ka1 to Ka2 to Ka3. And this is also due to the electrostatic attraction. So essentially in the end what ends up happening is H2CO3, it's easier to remove an ion, a proton from H2CO3 than HCO3. Now, and if you notice, obviously this acid is going to be significantly weaker than this one. This one is going to be more weaker than this. And this is obviously no longer an acid, but essentially the acidic strength decreases as it starts losing the protons. It doesn't want to let go, so automatically it becomes a weaker acid. Now, similarly, you have polyacidic bases. They're essentially the same. They have a tendency to accept more than one protons. Examples are CO3, 2 minus, which is the carbonate ion, C2O4 minus 2, this is the oxalate ion, and PO4 minus 3, which is the phosphate ion. So this can accept 3 protons, this can accept 2, this can accept 2 as well. So essentially the corresponding ionization constant for polyacidic bases would be KB1, KB2, and so on. That's it. So with that, I hope all of that made sense, and don't forget that basically in the end of this video, all you need to know is that you have some acids which have a tendency to donate more than one proton. Or let me rephrase this. The acids which have the tendency, which have more than one ionizable proton are called as polybasic acids or polyprotic acids, and polyacidic bases have a tendency to accept more than one proton. That's point number one. Point number two is you have something called as Ka1 and Ka2, which is first ionization and the second ionization constant. And the first ionization, as you go from Ka1 to Ka2 to Ka3, the ionization constant value decreases. And not just that, the third very important point is the fact that the acidic strength decreases as it donates more protons. So H3PO4 is more acidic than H2PO4 minus, which is more acidic than HPO4 minus 2. So essentially, as it loses more protons, the strength of the acid is also decreasing. In the next video, I believe we are going to be talking about the factors affecting acidic strength. I hope all of that made sense. Definitely comment if you need any help or if you found this video helpful.